Thank you very much. That's only one of the peculiar things about me. Okay, so at some point last week, I thought I ought to start preparing for this talk for PTAI. So I thought I'd better look at the email and find out what I'd promised Vincent I was going to talk about. And I thought, oh my God, why on earth did I say I was going to talk about consciousness, artificial intelligence, and the frame problem, which is a little bit like life, the universe, and everything. So I've abbreviated the title a little bit. I didn't tell him about this beforehand, so there's not going to be that much AI in this, although, of course, that is very much in the background of everything. Is there a pointer? Is there a laser pointer? Or
Take it out there.
is that, oh, okay. Is that okay?
Yeah, absolutely.
How do you turn it on?
Just plug it in your.
No, it's just for thing for the
Yeah,
the
you
board.
plug that into your.
Oh, do you?
Yeah.
Okay. Okay. Oh well, thank you.
Does it not come up?
Yeah. No, this we don't want to happen, do we? No, let's just get rid of that. But never mind. That's much better. That is much better. Okay, thank you, Aaron. That's much better. Yeah. Okay. Thank you. Okay. So okay, that's the. Let's forget about that slide. That's the topics I'm going to talk about. I'm going to be talking quite a lot about global workspace theory, which, as many of you will know, is one of the sort of leading contenders for the basis of a scientific theory of consciousness. And I'm going to be particularly relating that to the brain and to some neuroanatomy. And then I'll get on to talking about the frame problem. And there'll be quite a lot of neural dynamics as well. Okay, so first of all, global workspace theory. So as I just mentioned, global workspace theory has been gaining an increasing amount of respect and credibility as the basis for a scientific understanding of consciousness. And it has its roots actually very much in artificial intelligence and in a particular kind of cognitive architecture. So global workspace theory is Bernie Bars's theory, and it dates back to the late 1980s. And what he proposed was a particular kind of architecture, which is, if people have memories going back this far, it's sort of based on blackboard architectures, which were a kind of expert system architecture back in the 1980s. So the basis of the architecture is this. So you have a collection of parallel specialist processes and a global workspace. And the idea is that these parallel specialist processes all compete and sometimes cooperate for access, and I'll say what that means in a bit, for access to a global workspace. And whichever process or collection of processes wins access to this global workspace gets to broadcast out a message back to the whole cohort of parallel specialists. So in the original sort of architecture, this global workspace you can think of as a kind of repository of some kind of language-like representation, maybe, which is the thing that gets broadcast out to all of these specialists. And that's the that architecture that just has these elements is the basis of the whole theory, really. So we have these multiple parallel specialists competing and cooperating for access to this global workspace. Yep, so I've just said that. Yep. Okay, now, so have that architecture in mind, which is a kind of generic sort of parallel architecture, when you think about this. So this is the basic tenets of the theory. So you can distinguish the global workspace architecture, which has these parallel components, parallel specialists, and the global workspace. You can distinguish that architecture from an empirical theory. So the architecture has some interest as a cognitive architecture, even if you think the theory is wrong. But the empirical theory goes like this. Well, okay, so first of all, we can observe that the global workspace architecture harnesses massively parallel computation. So, and of course, the brain also harnesses massively parallel computation. And you should note also that the global workspace exhibits a serial procession of states, which we can think of as being a little bit like the serial procession of conscious content, perhaps. But the important thing, the power of the architecture, is that each state-to-state transition is the result of filtering and integrating the contributions of huge numbers of parallel computations. So now, according to the theory, there are really sort of three claims to this theory, or the second two claims are kind of go together. So according to global workspace theory, first of all, the human brain instantiates this architecture. So that's the first empirical claim. And then now comes the bit about consciousness, and this is the crucial bit. So the human brain instantiates such an architecture, and given that, we can make a distinction between, if you like, conscious processing and non-conscious processing going on in the brain. Or to try and express it a little bit more precisely, activity that is confined to the specialists does not contribute to consciousness, while the conscious condition is associated with broadcast. Okay, so that's really the essence of Bernie Bars's theory. He's drawing this distinction between localized processing in the specialists, which doesn't contribute to consciousness, but when you get broadcast, so going back a slide, so it's when you get this broadcast that's what's associated with the conscious condition, with consciousness. I should have flashed up a slide that shows you some of the empirical evidence in favor of this last pairing. So in particular, you can look, for example, at a paradigm where you have visual masking. And as maybe you're aware, if you use a rapid serial visual presentation paradigm where you have a series of images in rapid succession, then you can achieve this masking effect whereby you present, say, a word and then rapidly follow it by a visual mask, say a scribbled pattern, and then the subject can often not report having seen the word. However, the word still gives rise to priming effects for a later experiment. So perhaps the word was cat, and then if then on a subsequent part of the experiment, the subject has to do something where the answer is to say animal, then the subject is faster for having unconsciously subliminally seen the word cat. So you can use that kind of paradigm. You can manipulate the timings so that you've got a very, very slight difference between the presentation of the stimulus and the mask. You use that kind of paradigm to get two conditions, a consciously seen condition where the subject can report the word versus a condition where the subject is unable to report the word, but we know that the brain has processed it because you get the priming effect. So if you take those two conditions and you then compare you put your subject into a brain scanner and do some MRI, then you can compare the two conditions, and what you find is in the unseen condition where the subject can't report the stimulus, you just get localized activation in the visual areas, whereas when the subject is able to report the stimulus and is therefore being consciously processed, you get widespread activation elevated activation in areas all around the cortex. So that kind of thing is broadly supportive of this sort of empirical claim here. And there's a fair amount of experimentation along those lines that's been carried out. But what I'm really interested in here is I want to talk about how the human brain instantiates this kind of architecture, this kind of global workspace architecture. Because the way that it's described in Bernie Bars's original work is very much as a kind of theory within the tradition of cognitive psychology with lots of boxes, and it's kind of quite appeals to a kind of fairly classical view of the way we should build such theories, and it's subsequently been quite well updated to really to relate it much more closely to the brain and to the architecture of the brain. So in particular, Stanislas Dehaene and Jean-Pierre Changer proposed what they call a global neuronal workspace. So they were trying to bring out exactly what it means for the brain to instantiate this kind of architecture. And according to their ideas, the brain instantiates this global workspace architecture thanks to the cortical white matter. So this is a picture of the cortical white matter. It's actually my own brain. I used to put up a picture from a paper, but I've recently, had one of these things done at Hammersmith Hospital as an allegedly healthy subject, controlled subject, and so I can put up a picture of my own brain. So this is the cortical white matter, and these tracts that you can see are the long-range fibers that connect distant parts of the brain to each other. And according to Dehaene's version of global workspace theory, the global neuronal workspace really is a communications infrastructure that resides in the white matter. It's the white matter that enables broadcast. That's the essential, that's the essence of this refinement of the theory. So you've got a communications infrastructure which allows broadcast throughout the brain. Now we can start to explore that idea a little bit by using the contemporary, hot topic in neuroscience, which is connectomics. So something that people have been interested in doing for a little while is taking this kind of data here and turning it into a network or a graph. So the idea is that what you do is you take the cortical sheet and parcellate it up into different regions, and then you work out, for any pair of regions, you work out whether there is one of these long white matter fibre tracts that's connecting those two regions. And then that will give you a network. So the network is going to look something like this. This is from a very well-cited paper by Patrick Hagman and colleagues from 2008. So here, each of the dots is a node in the network, and that corresponds to one of these regions of the brain. And you see a blue arc between the two regions if a white matter tract exists between those two regions. And it's a weighted network. That gives you the width of the lines. Okay, so having turned this into this, we can now do all kinds of interesting mathematical analysis, because this is now a very easy to deal with mathematical structure. And in particular, we can look at certain properties which people who are interested in networks have formalized over the last few decades. So many of you will be familiar with the idea of a small world network. So a small world network, this is an example of a small world network. And in this small world network, we have high clustering, and that means to say that these nodes, if you pick out a neighbor of one of these nodes, then the neighbors tend to be connected to each other as well. So you have high clustering in that sense, but you also have a low mean path length. And what that means is that it doesn't take very many hops to get from anywhere in the network to anywhere else. And the reason for that in this particular network topology is because of these long-range connections that I've shown in green. Thanks to these long-range connections, you can take big hops across the network and then just a few hops to get where you want. And that, thanks to these long-range connections, that confers this small world structure on the network. So not very many hops to get from anywhere to anywhere. That's the essence of it. Now, so that's one kind of property that people who are interested in complex networks look at. Here's another one, modularity. So a network is modular if you can divide it up into collections of nodes that are densely connected to each other, but are much less densely connected to the other modules in the network. So this is an example of a modular network. This is not modular, but this one not obviously modular, but this one is. This is also a small world network because you've got high clustering, and also it doesn't take very long to get from anywhere to anywhere else in the network. So this is an example of a small world network. This is an example of a network that is a small world and also modular. It'll become clear why I'm telling you all of this in due course and how it relates to consciousness and the frame problem, I hope. Okay, so now we can also, in these kinds of networks, identify what are called connector hubs. So if we compare this one here with the one I'm about to show you, in this network, you may note that the connections between the modules come from all kinds of different nodes within a module, whereas in this one here, there are connector hubs. And these connector hubs are nodes that carry most of the inter-module traffic. So all of the traffic that's going from this module to the rest of the network passes through this connector hub. So you can also have a modular small world network with connector hubs. And if you have a modular small world network with connector hubs, then you can isolate those connector hubs and the connections between those connector hubs. That's this bit here, and that's what we call the connective core of the network. And this is often, well, okay, yeah, you don't need to know about this notion. A rich club is another measure that you can formalize in the theory of complex networks. Captures the similar kind of idea. Okay, so that's the idea of a connective core of the network. And I think you can kind of see that, you imagine that if this was a transport network, then this connective core of these nodes and their interconnection is going to be absolutely vital to the way the whole thing works, because everything is going to be, to use a metaphor I like, everything is sort of funneling into and fanning out from this connective core. Okay, now why am I telling you all of this? We'll come to that in a second. Well, the first thing that we need to note is that it turns out that the human brain is a network that fits that description. So it's a small world network with modules. So these are two figures from the Hagman paper, and this shows broadly how it's divided into very high level modules. So it's a modular network. It has that small world topology, and it also has connector hubs. And these red blobs in this diagram here are the connector hubs in the human brain. And so basically what you see here is what forms the connective core of the human brain. And it's a set of so this is the view from the top. So we're looking down from the top, and it's basically a set of medial regions which runs along the length of the brain, and that's the connective core of the human brain. And there's some later work that shows similar things. There's a good deal of work that shows essentially this kind of result these days. So this is very, this is a very beautiful result to have shown. And well, the reason that so just to kind of give away the punchline, which you sort of might, or one of the punchlines that you might have guessed, is that I'm going to suggest that this connective core, because of its topologically central position, is in a position to function like a global workspace. It's where broadcast can happen. But I just can't resist also pointing up this recent piece of work that I've done with some avian neuroanatomists, where we show that you get this connective core also in the avian brain, in the pigeon's brain specifically. And this is a diagram of the connectivity in the pigeon's brain. And when you do that kind of analysis, it turns out that, guess what? It's modular, it's small world, and it's got a connective core of hub nodes. And indeed, those hub nodes are the same set of, or are a similar set of cognitively important nodes that are the hub nodes in the human and macaque and cat brains as well. So there's some converging evidence that that these kinds of this connective core is present in brains that are capable of sophisticated cognition. Okay, so let me just go back 2 slides to impress on you to keep this kind of diagram in mind. So when I'm talking about a connective core, then this is the abstract, from an abstract point of view, it's sort of this bit of the network here, and that we can translate that into anatomy. In the human brain, case of the human brain, it's this set of medial regions of the human brain that are in this topologically central position. Okay, so now this is the sort of grand, or one grand claim, if you like. So the grand claim is that, so this is just a sort of abstract version of the diagrams in the Hagman paper, and this is showing this connective core. So what I'm suggesting, and which is very much along the same lines that I think Stanislas Dehaene is thinking, is that the connective core of the human brain is basically can function as a global workspace in the sense of Bernie bars. So it can act in particular as a locus of broadcast and competition. And those are the two essential features that you have in global workspace architecture. So there are a number of computer models that try to bring this out a little bit more carefully, and I can give whole talks on those. For example, Shanahan and his colleagues have produced so this diagram here is from one of Shanahan's papers, and as you can see, it looks very similar to my kind of diagrams. You have this central, topologically central portion here, and these more peripheral nodes here. And this is the global workspace in the middle here. And Shanahan and his colleagues have produced a very nice model of access to the workspace through competition between outlying regions. And I produced a model of the activation of the broadcast that's in the center of these regions. And that one is my model, which I'm not going to go into now. Okay, so I hope you got from that some idea of, first of all, of what global workspace theory is about as a theory of consciousness. And of course, this has been a very rapid presentation of the ideas, but I hope you've got the essence of it there. And also the idea of how that might map onto how the architecture that's at the heart of the theory might map onto the brain, and in particular to the connective structure of the brain. But now I want to, before I lead on to talking about the frame problem, I want to talk a little bit about the idea of a coalition of brain processes, because that's a kind of central concept, to what I'm thinking. I noticed that in the abstract to Dan's talk, I think we'll be talking about perhaps similar things. I don't know. Okay, so this is the way I like to think about the way behavior is produced by the brain. That it's generated by coalitions of coupled brain processes, where these brain processes might be sensory processes or motor processes or memory processes and so on. So you might draw it like this, that you have a collection of input processes and a collection of output processes, and they become coupled, and that's what produces behavior. So, for example, when a dog is following a scent along a path, then there's an input sensory process which is looking out for the scent and is constantly, through feedback, controlling the motor process that is keeping the dog, on the path of the interesting chemical trace that it's pursuing. So you have this coupling between these processes, a feedback-based coupling, and that's producing the behavior. But coalitions of brain processes are metastable. So that means to say that that as time passes, these coalitions will form for a while. They'll govern the behavior of the animal for a little while, and then as things change, then the coalition will break apart and a new coalition will form. And that's a competitive process. So when a new coalition forms, well, you really only want one coalition of brain processes to take charge of the animal and its body, because you don't want the animal trying to move left and right at the same time, for example. So only one coalition can eventually take charge. So there's a competitive element to this coalition formation, problem. Okay, so think of behavior in terms of the formation of coalitions of brain processes. Now we can think about and now we're starting to move towards the territory of the frame problem, because now we can start to think about some neural combinatorics. So this coalition formation problem is most challenging when you have got a combinatorial repertoire of processes. In fact, you can see this in the previous slide quite well, because you can imagine that let's suppose that behavior is formed by some combination of one or two input processes and one or two output processes. Well, even on this trivial little diagram, you can see that the number of possible combinations that you can have of that conform to that little description, is quite big, really. And of course, when you have literally tens of millions of brain processes that can form a coalition and govern behavior, then you've got a serious combinatorial problem. So this problem the problem of coalition formation is kind of easy when the situation calls for an established coalition, so a reactive kind of response, such as, for example, when the dog smells an interesting scent. But the problem is harder when planning is needed, when you have to think forward in time. And the problem is certainly hardest when a completely innovative response is called for. So there's this combinatorial challenge to this coalition formation problem. Okay, so I'm just telling you that as a kind of way of, as a sort of background framework for thinking of behaviour and how it's produced thanks to the brain. Okay, so with this idea of a coalition of brain processes in mind, then I want to put forward this connective core hypothesis, and you can read this paper in the Philosophical Transactions of the Royal Society, which spells this out in quite a lot more detail. So according to this connective core hypothesis, the connective core of the human brain, or indeed of the brain of a cognitively well-endowed animal, the connective core is a limited capacity, highly connected communications infrastructure that provides these three things: a locus of broadcast, and this, of course, it immediately relates it to global workspace theory, as we've discussed before, and an arena for competition among coalitions of brain processes, and a medium for coupling and communication between those coalition members. So I'm proposing that the white matter, and in particular the connective core within the white matter, can fulfill this kind of role. Well, not just the white matter itself, but the bits, the sort of nodes that the white matter is connected to as well. So now the interesting thing about this is that, as well as supporting a conscious-unconscious distinction, because this is basically describing how the brain can realize the global workspace architecture, how the brain instantiates global workspace architecture. So as well as supporting this conscious-unconscious distinction that the global workspace theory posits, it also promotes cognitive integration. And I want to say a little bit about what I mean by that. And this is where the whole frame problem thing comes in. Okay, so sort of remember this connective core hypothesis. Okay, so now when it comes to being, not just support. So think of this topologically central connective core, not just in terms of global workspace architecture, where it can potentially support the distinction between conscious and unconscious, processing. But I also want to emphasize its potential advantages from the perspective of high-level cognition and of cognitive integration, as I mentioned on the last slide. So that's a lot of what I want to spend the rest of the talk talking about. Okay, so what I'm suggesting is that this broadcast function subserves open-ended combinatorial coalition formation, and it's because this global communications infrastructure, that the connective core, can disseminate influence and information among otherwise independent processes. So the broadcast function is essentially allows any process in the brain to participate in the whole business of coalition formation. So it allows each of a system's components to influence and be influenced by the whole system. And I should emphasize, by the way, that this is kind of a high-level talk. So you're getting a lot of these sort of big claims, and there just isn't time in a talk like this to sort of give you models and empirical data that support these claims. So you'll have to you have to kind of indulge me a little bit, because each of these claims has usually got a computer model or that's been constructed either by myself or somebody else, or there are some empirical papers from neuroscience that support these ideas. So you're getting the kind of high-level picture here. So forgive me for a bit of the lack of kind of technical detail. Anyway, okay. So the claim is that this this connective core It allows each of a system's components to influence and be influenced by the whole system. And such a system will exhibit what people sometimes call dynamical complexity, which is a balance of integrated and segregated activity. And for those people who know a bit about this, about the scientific study of consciousness, you may be familiar with Giulio Tononi's ideas of information integration, and it's a consequence of this that it promotes high information integration as well. So, so that's sort of hints at the cognitive value of broadcast. Is basically it enables the whole brain to be recruited for the ongoing situation. So, in particular, if you have a novel or an unfamiliar ongoing situation, then thanks to broadcast, it makes it possible for any process to contribute to a coalition, a novel coalition, to address that unfamiliar situation. So that's the idea. Okay, now this broadcast mechanism is a limited capacity bottleneck as well. So this is another property of this connective core. Is that it's kind of there's not that much of it in a way. So this communications infrastructure can only really be this is another hypothesis, can only really be taken over by a subset of the brain, as it were. So it acts as a limited capacity bottleneck because only one coalition at a time can take charge of what the animal or robot does next. And so coalition formation has to be competitive, and you only want one winner at a time. I already mentioned that you don't want an animal trying to turn left and right at the same time. And this connective core enforces this kind of winner-takes-all property, because only one coalition at a time can dominate the connective core. And it also, as a consequence, enforces a kind of serial processing, because you have a kind of serial procession of broadcast states, or a serial procession of coalitions that dominate this connective core. So that supports the sequential chaining of mental operations, which is obviously something that's vital to high-level cognition. So we can say that the connective core acts as a bottleneck with a limited capacity, but it's a bottleneck in a good way, because if you weren't able to chain mental operations sequentially into a coherent sequence of thoughts, then you wouldn't be able to you wouldn't be able to come up with scientific theories of consciousness or with computers or anything. Okay, so to sort of give a summary of some of the two key ideas here. Okay, so the connective core explains. So if this sort of hypothesis is vindicated empirically, of course, which is absolutely vital. So you can see certain empirical underpinnings in terms of brain connectivity. So that's solid neuroscience. But obviously, there's a lot more to the hypothesis than that needs to be vindicated empirically. But if it's vindicated empirically, then this connective core explains perhaps the two essential features of consciousness: seriality and unity. So information and influence funnels into and fans out from this connective core, which is the same as this global neuronal workspace in Bars and Dehaene's theory, which acts as a limited bandwidth processing bottleneck, allowing for serial mental operations. So it gives you serial from parallel. And the second important property, the second important feature, is that it also promotes integration across the brain, so that a coherent response to the ongoing situation can be orchestrated from the brain's full resources. And in particular, it allows novel coalitions of brain processes to form. So you get a kind of unity from multiplicity. So these two little sort of sound bites, I think, are very important. Right, now, okay, so 33 minutes in, I make it, so now I can start talking about the frame problem. So now I want to try and relate that collection of ideas that you've just heard to the frame problem. Now, many of you may not even know what the frame problem is. So we're going to give you a very brief history of the frame problem. So in the 1960s, so this is a kind of, little bit of a lacuna in the talk. We're now talking about a different subject, but we're going to see how they all relate together in the end, hopefully. So in the 1960s, John McCarthy and Pat Hayes described this problem, which they called the frame problem, when trying to use formal logic to describe the effects of action. So they were working very much in this logicist paradigm of AI, and they were interested in trying to describe the effects of actions in the very precise language of first-order predicate calculus. And basically, what happened was that after quite a lot of teething troubles, logicians managed to find a way of overcoming this problem and solving it sort of in the 1990s. But in the meantime, a number of philosophers, including in particular Dan over here, saw a deeper issue in this problem that had been dug up by John McCarthy and Pat Hayes, and characterized a kind of deeper problem. So I'm going to talk very, very briefly about the logical problem, very briefly indeed, and then about the deeper problem, which is what I think can be addressed. Oh, and I should emphasize that Mike Wheeler down here wrote some great stuff on the frame problem as well, more recently. And I think that that the global workspace architecture addresses quite a lot of the deeper philosopher's version of the frame problem. Okay, so this is the original frame problem. So how can the effects of actions be described in a logical formalism without having to write out numerous formulae that describe the non-effects of actions? So really boring things like scratching my head doesn't cause the walls to change color. Now, this is the most boring fact in the world, and is nearly always true. But unfortunately, you have to, if you're writing if you're trying to describe the effects of actions in formal logic, you are obliged to write out lots of axioms that say this kind of thing explicitly. And this is really annoying. And what makes it especially annoying is that it turns out you've got to write out more of these kinds of things than the axioms that actually describe interesting stuff, like scratching my head makes the itch go away, for example. So there are loads more of these boring facts about the non-effects of actions than there are interesting facts. And so you really don't want to, if you're trying to formalize some domain, to spend all your life as an AI programmer writing out pages and pages and pages of formulae of this sort, right? So that's the frame problem, according to the original version of the frame problem. Now, after quite a lot of work in formal logic, people working in the area, and I was one of them, came up with a pretty much a solution to this. And it's basically what you want to do is you want to say that you want to assume that things stay the same unless the logic dictates otherwise. And logic doesn't allow you, ordinary logic doesn't allow you to say that, but you can use a non-monotonic logic to be able to say that. And so what people in the sort of theoretical end of AI in the 80s and 90s spent a lot of time doing was working out how you could get non-monotonic logics to basically say this kind of thing, that assume things stay the same unless there's a reason to suppose otherwise. And one way of doing that is using predicate completion in logic programming, for those people who know that stuff. Okay, so that was sort of the original problem. That's the sort of pretty much solved it as it was originally stated. Well, I would say so anyway. But in the meantime, as I mentioned, the philosophers had discovered a lot of, the philosophers had discovered what they saw as a deeper problem, and Dan Dennett takes particular credit for pointing this out. And so this is what the sort of philosophers saw. Well, suppose, so they saw that version of the frame problem is in a sense an instance of a larger problem. Suppose we're building a robot that decides what to do on the basis of a representation of the world. So that's the kind of classical AI premise. Well, how does a program maintain its model of the world? How does it maintain its set of beliefs about the world in the face of change? In particular, how does it work out what beliefs to revise without considering everything it believes, its entire knowledge base, and all of the implicit consequences of the things it believes as well? And Dan has a very nice example involving a robot pulling a bomb out of a room that shows how all the, what you think of as the obvious answers to this, to how you might do this, turn out to be sort of not really terribly viable when you go a little bit deeper. And then along came Jerry Fodor, and he sort of generalized this even further, really, by saying, well, more generally, how does a program determine the set of beliefs that are relevant, and this is in orange for a good reason, that are relevant to some ongoing cognitive function, such as belief update, or any other cognitive function that you can think of, such as analogical reasoning, working out where that the structure of the atom is like the structure of the solar system. How did anyone ever come up with stuff like that? You've got to work out that two things in totally different domains are relevant to each other. So how on earth could a program ever do that? And then, as Dreyfus then sort of put it, well, the trouble is that everything is potentially relevant to everything else. So how on earth will you ever write a program that is as smart as a human being when we can realize that the solar system is like, or the structure of an atom is like the structure of the solar system, and many other examples of that kind of reasoning that we carry out in everyday life, putting together things from completely disparate domains, potentially, when you think about that kind of cognitive operation, everything is relevant to everything. How on earth are we ever going to address the combinatorics that implies? And I realized to my horror, I've only got 5 minutes. No, I've got 10 minutes. I've got 10 minutes, according to my clock, actually, of elapsed time. Okay, so there are some very nice examples of this, even in the animal kingdom. So this is one of Aaron's favorite examples, and one of mine too. This is Betty, the celebrity corvid, who I believe she's passed away, and I believe she's in a cabinet stuffed somewhere not very far from where we are right now. But Betty was a star, and she. So the extraordinary bit of behaviour that she displayed was this. So I'm not going to show you the video. I think probably many of you have seen it anyway. So inside this transparent tube is a little bucket with a handle on it that's got food in it. She can't pull the bucket out with her beak, but she knows that she can pull it out with a hook. And so she was able to do that. But the remarkable bit of behavior was that one day, without any prior experience of this situation, there was no hook in the enclosure, just a piece of straight wire, and Betty spontaneously bent the piece of straight wire into a hook and then used it to pull the bucket out of the tube. I'm sure you've all seen the video. It's completely wonderful. And so in cases like this, how on earth does the brain, even of a crow, entertain the necessary novel coalition of processes, to think of it doing a thing like that? So I should just skip that one. So this is some animal cognition researchers have characterized it in this kind of way. So. And I particularly like this way of putting it. So this kind of innovation is the spontaneous interconnection of two repertoires of behavior which have been established separately. Now this entails, this ridiculously wide search tree. Well, actually, I haven't got time. Okay, so this is meant to show the affordances of Lego bricks. Well, I can sort of put them together into these kinds of combinations, and then I can assemble those into different. And of course, just with Lego bricks, you have this vast space of possible things that you can do with a set of Lego bricks. It's combinatorially explosive. Well, you haven't got an infinite number of Lego bricks, but even so, it's daunting. But just think if you have to include in this kind of thing, where you have to think of putting together two completely unrelated behaviors. So this is my son, when he was a bit younger, realizing that he could use a catapult to launch one of these assemblies of Lego bricks, and thereby annoy the cat. Well, this is kind of annoying for the cat, but it's a kind of a little stroke of genius in a way that kids carry out all the time, connecting completely different bits of behaviour and coming up with a completely novel coalition that can give you a completely new form of behaviour. Now, this isn't solving any problem, but particularly, but in the case of Betty, you know, that was brilliant. It sort of solved a problem. So the big question is, how is it that we can solve this kind of problem in the brain? And that's where I think the global workspace architecture and the way that it's instantiated according to the connective core hypothesis can help out a great deal. So the problem is that everything is potentially relevant to everything. So how could a system possibly search every combination of everything with everything, every possible coalition? Now, of course, in classical AI, we do search through combinatorial spaces all the time. You know, in everything that's in Russell and Norvig, you know, there's plenty of examples of things that search combinatorial spaces. But the most challenging form of this coalition problem is where the constraints and goals, you know, are just unknown, are completely unknown. And all the system can really do is sort of try out random combinations, or this is the way you might think of it. Just try out random combinations and see what happens, you know, see what reward you think you're going to get. Okay, so in the last 5 minutes, I want to try and say how I think the global workspace architecture can support this sort of thing as well. So there are two stages to coalition formation where the global workspace architecture helps. So the first is in establishing potential relevance. So processes that are potentially relevant to the current situation are going to, you want them to be alerted, as it were, to become active. And the idea is that all such processes are reached thanks to the broadcast mechanism. And the second one is, well, how is it that coalitions of jointly relevant processes form? So how do they kind of get it together out of this vast pool of combinatorial possibilities? And this is where the combinatorics kicks in, and where you need the right kind of neural dynamics to address this sort of problem, which is also something that is helped by this connective core architecture. But I think I'm not going to quite get to being able to tell you the details of that, unfortunately. But first of all, potential relevance. So now, when Fodor characterizes the frame problem, so he really does seem to have this rather serial kind of architecture in mind when he describes it. And it's something along these lines. You've got some kind of central processing going on that's saying, oh, are you relevant? A, no. Are you relevant? B, no. Are you relevant? C, no. And if you've got billions and billions of processes, well, that starts to seem computationally challenging. It seems less so perhaps now than when Fodor originally described this aspect of the problem. But anyway, global workspace architecture certainly helps out here because it offers a parallel alternative. So the idea is that information about the current situation is broadcast out to the whole cohort of processes. So in neural terms, this is via the connective core. So all parts of the brain can be influenced by what's going on in the connective core. And then those parts of the brain can then ask, they're acting sort of semi-autonomously. They're saying, am I relevant? Am I relevant? This is like the Catherine Tate version. Am I bothered? Am I bothered? Yes, I'm bothered. And so this one is going to say I'm relevant and is in a position to start contributing. And of course you have a huge cohort of these specialist processes. So many of them might can say, oh, I'm relevant. So that's how you can address the problem of potential relevance. And 2 minutes. Now, the second part of the problem is so imagine that then you've got a large pool of processes that are sort of woken up and active. Then how can they get it together into a novel coalition when you still got some daunting combinatorics? And I think the residual daunting combinatorics is probably what Jerry Fodor had in mind, although it wasn't I found it not very explicit in the paper. But then reading other people such as Dan and Dreyfus and so on, and Mike's work makes it kind of clearer, I think. So this is how the kind of coalition formation goes on according to this global workspace architecture. So this is your global workspace, your connective core. These are all of your parallel specialist processes. And so this green hue here is meant to represent information that's been broadcast out to all of these broadcast out, and then you've got this green coalition has formed. So, sorry, I should put that the other way around. The green coalition has formed. That's taken control of the global workspace. So the influence of this green coalition is going to be permeated out throughout the brain. Now on my screen here, there's a nice light green hue all around here, which indicates the broadcast, but that's completely not come out on the screen here. So you have to imagine this light green hue is sort of out here as well. So the idea is that now this light green hue, which represents the influence of this previous coalition, has now been broadcast out, and now you've got a number of potentially relevant processes. And they're all jostling together to try and form a coalition to take over the workspace. And this is what has happened here. So now this purple coalition has taken over, and now you've got this sort of cycle of broadcast and competition and broadcast and competition. So what we're interested in now, so this was the establishing potential relevance, is the dynamics behind this coalition formation bit. Okay, so 1 minute, right? So it's this bit here. It's this bit here. Okay, so the difficulty of assessing potential relevance is diminished by broadcast, but how can these previously unrelated processes come together in the same coalition? So in order to get this kind of joint relevance, then you need a system with the right sort of dynamics. And I'm just going to be able to hint at this, unfortunately. So all I can say is that suppose that you could try almost every combination of everything with everything else. So perhaps this is really only possible in a dynamical system that is sufficiently sort of holistic, in scare quotes, where every process exerts a little tentative influence on every other process. And then processes can then coerce each other into alliances, and then the alliances can compete, jostling for dominance, and then larger process alliances can then take shape until there's an overall coalition that dominates the dynamics of the whole brain through the connective core. And then there's sort of another 10 minutes on what sort of dynamics can support this and how the connective core is very important for that. But I think I'm just going to have to hope that Dan's going to say something at the end of the day which will be compatible with this. But his abstract hints that he will. So I'm just going to skip then to a concluding my concluding slide. Concluding slide. Okay. So in the brain, there's
there and have a little discussion.
Okay. Well, you want to? Is that? Okay. Yep. Okay. Well, okay. I'd rather leave that there because that's the book you should all read.
All right. Let's thank the speaker.